I'm going to talk about simulation in this lecture. Simulation is a very important topic for statistics and for a number of other applications. So I just want to introduce some of the functions in R that can be useful for doing simulation. So there are a couple of functions that are available for simulating numbers or variables from given probability distributions, probably the most important of which is the normal distribution. And so we can generate variates from the normal distribution by specifying a mean and a standard deviation for that distribution, and then calling the rnorm function. So the rnorm function will simulate normal random variables from a distribution that has a given mean and standard deviation. There are corresponding functions for the normal distribution that can be used to evaluate the probability density, to evaluate the cumulative distribution function, and also for evaluating the quantile function. So another function for generating random variables is the rpois function, which generates Poisson random variables from a Poisson distribution with a given rate. So there are a number of functions for generating random variables from kind of the standard probability distributions, and you can use these to run simulations. So probability distribution functions, there are basically four functions associated with them. And so for any given distribution like the normal distribution, there will be a function that starts with the D, a function that starts with an R, with a P, and a Q. So there'll be four different functions for each distribution. So I've already mentioned that there's the rnorm function. So the rnorm function is for random number generation. There's a dnorm function which evaluates the density of the probability distribution for a given mean and standard deviation. There's the pnorm function which evaluates the cumulative distribution, and there's the qnorm function which evaluates the quantile function. So every distribution has these four types of functions. So for the gamma distribution, there will be a d gamma, an r gamma, p gamma, and a q gamma function. And for the Poisson distribution, there's the r pois, d pois, p pois, and q pois functions. So working with the normal distribution requires these four functions. So I mentioned there's dnorm, pnorm, qnorm, and rnorm, and you can see they each take a number of different parameters. All of the functions require that you specify the mean and the standard deviation because that's what specifies the actual probability distribution. If you do not specify them, then the default values are a standard normal distribution which has mean 0 and standard deviation 1. For the dnorm function, you can evaluate the density, and there's an option that allows you to evaluate the log of the density. Most of the time, when you evaluate the density function for a normal distribution, you're going to want to use the log of that value, but the default is false. For the pnorm function and the qnorm function, there's also an option to evaluate it on a log scale, but another option is whether or not you want to evaluate the lower tail of the distribution. So the lower tail, which is the default, if you look at the probability distribution, it's the part that goes to the left. It's the lower tail. If you want to evaluate the upper tail, sometimes you want to do this. Then you want to say lower tail equals false, and that will evaluate the upper tail of the distribution. And finally, for rnorm, there's only two parameters, mean and standard deviation, and then n, which is the number of random variables that you want to generate. So if n is 100, you'll get a vector of 100 numbers that are drawn from the normal distribution. So just to be more explicit, if phi is the cumulative distribution function for the standard normal distribution, then pnorm is equivalent to phi, and qnorm is equivalent to the inverse of phi. So just quickly, if you want to generate some random variates, you can just call rnorm and pass it an integer, which is the number of variables you want to generate. So here I'm passing 10. And you can see that the vector that's produced will be random normal numbers which have mean 0 and standard deviation 1. If I wanted to generate a vector that had mean 20 and standard deviation 2, I just need to specify that explicitly in my call to rnorm. So here, this vector has are 10 random normal random variables, and their mean is roughly 20, and their standard deviation is 2. So anytime you simulate random numbers from any distribution for any purpose, it's very important that you set the random number generator seed, and this can be done with the set.seed function. So what's important to know is that on computers, when you generate random numbers, the numbers are not actually random, but they appear random, and that's the important thing. And so the idea is that if you wanted to generate the same set of random numbers again, you could if you wanted to, because the numbers are not actually random. They're what are called pseudo-random numbers. And so here I'm setting the seed to be 1. So the seed can be any integer you want. You just pass it an integer, and that's the seed. So here I'm going to set seed equal to 1, and then I'm going to generate 5 random normal random variables. And so here I've got my 5 normal random variables. They have mean 0 and standard deviation 1. If I generate another 5, you'll see that the vector is totally different because it's another random sample of 5. However, if I reset the seed to be 1 and I draw 5 again, you'll see that they're exactly the same as the first 5 that I drew. So when you set the seed, it kind of sets the sequence of random variables that's going to occur. And if you reset the seed, you kind of set the sequence to go back to where you started, and then it will continue to kind of generate random variables from there. So this is important because it allows for you to reproduce the random numbers that you generate. Now that might sound strange, because why would you want to generate the same random numbers twice? But in many applications, you do want to generate the same random numbers twice so that people can reproduce what you've done. And in particular, if there are some errors or problems in what you've done, you want to be able to get to kind of go back to the exact situation that produced those problems. So whenever you do a simulation, you always want to set the random number seed so that you can go back and get the same results. So I've demonstrated how to generate normal random variables, but of course you can generate random variables from other probability distributions. So the Poisson distribution is of course very popular. Here I'm generating a 10 Poisson random variables with a rate of 1. So of course Poisson data are going to be integer. Here I'm generating 10 Poisson random variables at the rate of 2, so you can see they're slightly larger. And then here I'm generating 10 random variables, Poisson random variables with a rate of 20. So for the Poisson distribution, the mean is going to be equal to the rate. So you can see that roughly in each of these 3 cases, the mean is roughly equal to the rate that I specified. I could also evaluate the cumulative distribution function for the Poisson distribution. So here in this first example, I want to know what is the probability that a Poisson random variable is less than or equal to 2 if the rate is 2. And so this is the probability, it's 0.67 roughly. If I want to know what's the probability that a Poisson random variable with rate 2 is less than or equal to 4, you can see the probability is getting bigger. And here I can see the probability that a Poisson random variable is less than or equal to 6, and it's very close to 1. So the cumulative distribution allows you to evaluate these probabilities.